we're going to do something now for something slightly different. Okay? And so I just want to back us up. Remember when we took multiple diodes and stacked them as such? Okay? And we said these are each 0.7 volts. And we put a resistor up here, and we put 10 volts up, and we grounded this side. And we said this is always going to stay really close to 2.1 volts until, you know, we can vary this resistor and it doesn't really matter. We can actually pull current off of here. At a certain point, there's going to be breakdown, but that's always going to be 2.1 volts. And I said this is something like regulation. And I just want to point out something, what exists in the world today. This is the out, the in. Let's say this is a 7805 regulator. You can get these, and these are really common. If you go down to the dollar store and buy a USB adapter, or USB adapter for your car that plugs in the cigarette lighter, it has something similar to this in there. I've cracked them open, and they have actual 7805s in there. And the trick with this is we can put in 12 volts, so we can put in 12 volts here from your car. And on the other side of this, and they have you usually need capacitors to do some smoothing for us. But then we have 5 volts. For 7805, it will be 5 volts. This indicates how much output voltage is 7815, outputs 15 volts. 78M33 outputs 3.3 volts. But this will output 5 volts on this other side. And so this is what we call a voltage regulator. People with who work on their own cars recognize that there's a voltage regulator someplace, either related to their alternator, or inside their alternator someplace. There's a voltage regulator that it changes the voltage that comes out of the alternator into something that the battery likes. And so that's what voltage regulators do. The way that they do them is the typical one, 7805. They just waste heat. And so imagine this. This is how the 7805 works. Here, so we have 12 volts that goes in. This is our load. We'll put it to ground. This is our load. Okay? And what it does is it measures this voltage and varies that resistance. And it measures this voltage with respect to ground and makes sure that this is always 5 volts. And then it just varies this resistance that's up above it. Now, it doesn't do this in this manner. It doesn't actually use a potentiometer to do this. It uses a transistor. But it does this kind of operation. So if we have 12 volts coming in, that means this is 7 volts, and over the load is 5 volts. And this is just giving you an example of how this is laid out. And let's just say that this is a 5 ohm resistor. And so that's going to be one amp that's cruising through all of this. That means here, how much power is being here? So power is equal to IV, and that's going to be 1 times 5 watts. So we're dumping 5 watts to our load, but that means there's 7 watts up here that's just turning into heat. And so these sometimes get hot. There are more efficient types of regulators than this that use switching, but you don't have to worry about those. They're much more noisy, but actually getting to be much more common because they're so small and so efficient. They don't get hot. They're like 99% efficient. But this one you can look and you can do the calculation. What's our efficiency? You say 5 over 12. That's horrible. That's less than 50% efficient on this conversion. Luckily, it doesn't take much to charge your iPhone in your car, and so there's so much other waste in your car. You literally have a radiator that's sucking energy away from the engine and radiating it off as heat. And so literally, your car is wasting so much energy in so many other ways that we don't care about this piddly amount, the 7 watts that's here. There are hundreds of watts in your car that are just being floated out into the ether. And that's why electric cars can be that much more efficient. is because they can gather up that energy. They don't have an internal combustion engine that's heating up and just giving off free energy out into the atmosphere. But so that doesn't really matter. It matters for size. You don't want something hot that's in your car that's sitting there putting off a lot of heat. And so the really nice ones will be more power efficient, and they won't get hot. If you do space type applications, making a little satellite or something like this, you never want to have this because you only have radiation or convection. You don't have conduction through the air because there is no air. And so you have to worry about that when you start doing space type stuff. Ours is a little bit different, and that's where ours is a little bit different because we stacked up these diodes like this, and I know this is, and we can stack up enough to get 5 volts, but I'm only going to do the 2.1 volts here that we have because it gets tedious on lots of things here. But over here is where you put your load. Okay, and so we charge up whatever works on 2.1 volts off of these 3. At a certain point, you can draw so much current here that no current that it bypasses these guys and actually will drop the voltage. It will drop the voltage because this basically treats these as an open circuit. Okay, they become marginally biased. And this treats these as an open circuit, and then you end up with just a voltage divider. Okay? Up until that point, these don't look like, and I drew these wrong, so my apology. It was like this, wasn't it? Okay, so there's a point where you can get these marginally biased because so much current draws this way, and nothing goes through the diodes, and this just becomes a voltage divider between these two guys. Okay? Well, that's not very good, and the way that we're going to do it isn't very good, but what we're going to do is we're going to introduce to you this. This is a Zener diode. The Zener diode is designed to non-destructively break down in reverse bias at a specific voltage. Okay, they make these at different levels, but let's just play with this a little bit and look at, I suppose where we have to look is we have to look at the breakdown curve. And so if we come over here, so here's where we did a little whoop, there's our exponential where we have our VD on our horizontal axis and V and I. And this guy comes over here and a Zener diode breaks off right here at some point. Okay? So we need to examine this area. We're going to say this is really close to a straight line as it drops off there. It's not vertical, but it's asymptotically falls off. We have a little bit of a corner here that we have to worry about, but we just want to model it. We don't want to do all the math. We don't want to call it an exponential. And so let's zoom in on that just a little bit. Okay, and this is in reverse bias. So that's what happened there is I'm just going to put a resistor in here. We're going to do a variable voltage, and as we increase the voltage, there's going to be a certain point where all of a sudden that thing opens up and it turns on. There's lots of uses for Zener diodes out there actually, and that's why we're spending just a little bit of time on them. But let's blow this up this way, and we have this guy, and let me do this where it actually looks like it. Okay, I think that was pretty good. Okay, and there's a few things that we can say here. There's a line here that I'm going to call VZ0, negative VZ0. There's one here that I'm going to call negative VZK. Okay, and there's a voltage here, which we're just going to call VZ. That's the Zener voltage. There's the slope of this line, which we're going to say is 1 over RZ. And I think we have everything that we care about there. And what we do is the model that we have for this, for that Zener diode, is that in reverse bias, so as it is here, is it looks like a voltage source in series with a resistor. We call this VZ0 with RZ. So if this is biased beyond VZK, okay, if we bias this voltage, if this voltage is greater than VZK, then this Zener diode here we can model it just with this, but we have to know these two values. And this is going to seem a lot more complicated than it actually is, but this is really simple. All we need to know is slope and intercept. That's what VZK is. We need to know those two things, the slope and the intercept. Okay? And actually, this is the intercept right here. It's not VZK. I don't have this drawn perfectly as it should be. And so our VZ is equal to VZ naught plus RZ times IZ. Let me do this right. Plus RZ times IZ. Okay, so we're just doing a straight line approximation from this. And so we just, the trick on this just seems like kind of an exercise, but we need to figure out the relationship between VZ, between all of these different things. And the way we do this is with test voltages of whatnot, okay? And so what they're going to do is, let's do an example. I think we need to do an example, and so let's just start off with one that they have here. And they say something like this. VZ is equal to 6.8 volts. By the way, you can get Zener diodes in all sorts of different voltages. They work great for safety. They have a test voltage, some IZ. So they've tested out here, they've said IZ at some point is equal to 5 milliamps. Okay? They also know what VZ is, which is what the Zener voltage is. And they also say RZ has been measured to be 20 ohms. Okay, so not super crazy. And then we also have an IZK, which was the current where the VZK happened. IZK, in this particular case, is equal to 0.2 milliamps. And so it's just kind of a game of figuring out what information you have and what you don't. The supply voltage is 10 volts. It can vary by plus or minus 1. Find V out with no load limit. So what they've got is, let me draw the circuit that they have for this thing. They have, and this is a regulator circuit, 10 volts plus or minus 1, bias resistor, Zener, ground. Okay, so that's what that looks like. We're going to come over here, drop in an R load. Okay, and I think that they told us what we have for. Yeah, they didn't tell us this except in the picture, but they said this is 500 ohms, and it has all these other characteristics. And so, the first question that we have is find V0. Okay, V0. If you paid attention to it, V0 is just, or V out is just the voltage here. And V0 at no load, okay? Find 0 with no load, and V plus that's nominal, and we have this information, okay? And so what we do is, because of the equation that we had before, we need to find out what VZ0 is, okay? And we don't know what that is. So we need to figure out what VZ0 is, okay? And the way that we're going to do this is, it's basically going to be where this asymptote crosses that line. Okay? So this is just a point slope type thing that we have in relation to this. And so we know, so y is equal to mx plus b. That's all this is. But we have to just map things correctly. So this gives us a, let me see. These two were tested at the same place, and so that gives us 6.8 is equal to resistance times current, so 5 milliamps times the Zener resistance, which was 20, plus the plus whatever offset there was. And this is going to be our VZ0. That seems kind of rudimentary, but we end up with VZ0, 6.8 minus 0.1 volt. Yeah, you can put those together. That gives us 0.1 volt, 6.7 volts. Okay, so what we can model this with now is this is no longer a Zener diode. This is a voltage source that's 6.7 and a resistor, and these can swap around, of 20 ohms. And that just turns this into a problem that we can play with. So nominal voltage, so what they want here is they want to know what V out is, nominal voltage 6.8, and this turns into pretty simple, 10 minus 6.7, okay, is going to give us whatever voltage is going to be across these two resistors, okay. 10 minus 6.7, that should give us 3.3. Is that right? Yeah, 3.3. Okay, 3.3 times 20 divided by 520. I'm just doing a voltage divider between these two. Remember, our load is open. Okay, and that gives us whatever this is here, and then we're going to add it to the 6.7. Okay, so 3.3 times 20 divided by 520. It's going to be a small amount. 1.126, and then we have to add back in the 6.7 volts here. That gives us 6.827. That's what the voltage would be for this particular setup. Okay, and so I skipped a lot of steps to this, but this is basically voltage regulation. What's really cool about this is if you change this, even significantly, nothing really changes. This voltage is going to go up just a little bit. The book does a few more examples, and you find out that we get like 20 millivolt changes, and they do something called voltage regulation. And so let's just take a look at that really quickly here. They have this plus or minus 1 volt. So the next question is find the change in V out resulting in plus or minus 1 volt. Okay, so this becomes 11 or 9. Okay, and I should have just written a MATLAB program to do this, but we can do this really quickly, which is 10, 11, or 9 minus 3.3 is equal to those two voltages. 2 volts different. Okay, and I hope you can see it on the MATLAB there on the right-hand side. And then we take that voltage, and I multiply it by our 20 ohms divided by our 520 bias total. And that gives us that difference, amps plus 6.7, which is this voltage here. Okay, and that gives us 6.9962, 6.9192 to 6.19. So I did something wrong because 6.827 should be in between both of those. Let's go up and see what I did wrong. I'm going to do all 3 voltages. 10. And maybe it was that when I did 6.7. And then, let me see. I think, I did minus 3.3. Ha! There. Solved. 6.7. That gives us all those voltages: 4.3, 3.3, 2.3 volts. And then we're gonna combine those in. We're gonna multiply times 20 divided by 520. That's gonna give us our voltage difference because of that resistor, the Zener resistor, that 20 ohm Zener resistor. And you can't quite see it on my scroll. That 20 looks like a 10, but that's actually 20. And then we're gonna amps plus 6.7 volts, and that gives us 6.8, 6.7. So not a huge amount of change. When we talk about voltage regulation, the question is the delta V divided by V plus. Okay? Our delta V is going to be the 6.8 amps of 3. Can I do that? Minus amps of 1. I think those are right. I've been doing too much C, minus amps of 3. And that gives us 0.769 amps divided by our 10 volts. And that gives us 0.77%. And when I look at this in the book, let me see. B regulation 38.5 millivolts. I think that's half of what I've got here. So you do the average. So plus or minus 38.5 millivolts. Yeah, so 77 divided by 2 is 38.5 millivolts. That's a line regulation that we get out of that. So that's not much. We changed the top by 10%. The bottom we got a 0.77. It's a small amount of regulation that we have out of that, which is really good. I don't think we're going to go on to C, find the V out resulting from. So once we add on a load, we can start getting a second current pathway, and that can change things. There's a certain point where this voltage regulator, this voltage divider, there's a certain point where that cuts this off. It gets below our knee voltage for voltage. And so we can find what that is here really quickly. Let's do that, and that'll be the last thing that we do. And what we want to know is we're going to want to know when V out in the voltage divider is going to get below 6.7 volts. Okay? So when V out is equal to 6.7, which is going to equal 10 times, and remember that means that all this is cut out, is equal to RL over RL plus 500. And this just becomes 6.7 times RL minus 10 times RL is equal to, let me see, minus 500 times 6.7 times 6.7. So we can crack that out in MATLAB here really quickly. Let me see if I can do this in the short amount of time that I have here. And so this ends up being 3.3 times RL, 500 times 6.7 amps divided by 3.3. And so it looks like at about 1 kiloohm, those guys, that thing will start falling apart. Okay? And let's test that. Let's do 10 times 1K, 1e to the third divided by 1500. And that gives it, 6.66 volts, so right around 1K. If our resistance gets too much lower than 1K, the voltage regulation will fail. And so that's how these voltage regulators work. Nobody does this, by the way. We do not voltage regulate with Zeners. And the reason why we don't voltage regulate with Zeners is because they're hugely inefficient. They're less efficient than the first method that I showed you with the 7805 regulator. I will show you in the future some other options we do with Zeners, because Zeners are very helpful for other things, mainly protection.